So again, this is research method in computer science. Actually, it's HCI, human-computer interaction. Lecture number 2, experimental research. So we mentioned about significant test, which is the same as hypothesis testing. So this is one of the traditional statistics method of testing. Testing a sample if it's the same as a previous knowledge of the population. So yeah, we go through types of behavioral research. Research hypothesis, we discussed that already, so we just go a little bit quicker here. Then also we talk about basic of experimental research. Then we're going to talk about the limitation of experimental research. So research method in, again, computer science, when studying interfaces and applications. Here is human-computer interaction studies. So when we are studying interfaces and applications, these are some of the studies we can use. The first one is observations. So observations basically is based on we are observing participants. Human-computer interaction, we are trying to find out if we can come up with some method or some tools or devices that participants can interact with a computer more easy. And the previous example I gave was if I develop a nice computer game for children between the age of 6 to 12, the learning curve of the game shouldn't be too high. Children don't have patience to learn something new for a couple of weeks or days even. So we want to make the learning curve very quick, slow. And also the interaction between the children and the game. The learning curve should be as easy as possible. So we need to, first of all, we create a game, we create how the users are going to interact. We can do a research first before we put it in the market. Every software we develop, it can be in business application, medicine, scientific, it has to go through testing procedures. And we have different types of testing, from unit testing, integrated testing, alpha testing, so many different types. Even that we can test in class level, module testing. So different type of testing. So observation goal studies is to monitor how users interact with the computer based on their age group or the characteristics of the participants, women, men, education low, high, etc. So that will be an example of observation. We observe what the users are doing. And here again, we are trying to explain it in terms of computer science applications. But we know in the medical field also the same thing. We can give patients some medicine and observe them for some time and see how the medicine we have, how they are going to react, is going to react in their body, etc. We also have the field studies. We also have surveys. So surveys can be questions we give to the participants after they play the game finish. Maybe we can even give them a survey to see how their interest of the game, how they feel about it. And the usability studies also the same thing. The game, we give them the game to use it, to play with the game. Then we see their outcome, their whatever they feel. We also do interview studies, focus group, and control experiments. So all these studies or research methods can be done using, if we are in the field of computer science or human-computer interaction. So research method, we can choose, as we saw the previous, we have different research methods. We can choose any of the method based on the primary purpose of the study. What is the research objective, goals? So the primary purpose of the studies may decide what research method we should use. Also the time constraint. If I have a research to do and I have only 2 weeks, I don't want to monitor the participants for 1 year to find out the interaction with whatever intervention or controls I have. I don't want to, we have to go with the time constraint. And also the funding. And also people are the participants pool, they are variable participants. So these 4 or even more can determine the type of research method. But I think the primary one will be the objective, the purpose of the study is the first may determine. Then, of course, if we have enough time, we have enough funds, we have participants pool, we have resources, logistic, etc. Then we may decide which one to choose. So when it comes to behavioral research, we have 3 types. So we have the descriptive investigations. This is almost the same as what we mentioned about fundamental research. So descriptive investigation, you are not going to find a relationship between 2 variables or the reason why something happened. No, we're trying to understand the phenomena or construct a new theory on it. So here, descriptive investigation is constructing an accurate description of what is happening. So that can be one type. The second is relational investigation. Here it's like finding the relationship between 2 variables or more, or the causal relationship if one causes the other. So this would be using analytical skills. We spoke about independent variable and a dependent variable. We have confounding variable, modification effect or moderators, etc. So we'll find the association or causal relationship. Then we have experiment. Experiment is very good if I really want to be 100% sure that the relationship between the 2 variables, they have a causal relationship. Because in the experiment, I'm not going to observe no more. I'm going to do it in the lab. So experiment automatically removes confounding variable. Now we have another term called residual confounding variable. Residual confounding variable is the confounding variable that exists in your research, even after you try to eliminate all the confounding variables. So most of the time in observational research, confounding variable always exists. Our goal is to minimize it. But when we are doing experimental research, we 100% establish the causal relationship. Confounding variable will not be around because here we're doing hands-on now in the lab. If we have a dosage of medicine, we give to a person or in a lab, biological person or whatever we give, then we'll get the result straight. There will be no confounding variable there. So those are the 3 types of behavioral research: descriptive, relational, and experimental. It's almost the same as our textbook mentioned, but in a different way here. So these are the examples. In a descriptive, as we said earlier, describe a situation or a set of events. You don't want to know the reason why, or we don't want to find the relationship between. The example will be S is happening. But we can see in relational, X is related to Y. We want to see if there's a relationship between X and Y. So here we identify relations between multiple variables. Now with experimental, the cause is S responsible for Y. So we're finding the causal relationship. Here we are 100% sure there's no confounding variable. So this experimental is a controlled experiment. With relational, it can be observation, it can be field studies, it can be also be survey. With descriptive, we can use observation, field study, focus group, or interviews also. We spoke about research hypothesis, same concept here. So an experiment normally we start with the research hypothesis. Actually, we start with the research goal. From the goal, we can come up with research questions. From research questions, we can formulate the research hypothesis. So hypothesis is a precise problem statement that can be directly tested through an empirical investigation. And hypothesis is again very smaller in terms of the general objective of the research. So it will be more focused statement that can be examined by a single experiment, like using the test statistics, we test the hypothesis, null hypothesis, only once. The result we get on P, either we are going to reject or we accept the HO. So types of hypothesis, we mentioned the null hypothesis. That is the claim. So here we say there's no difference between the experimental treatment. Null hypothesis typically state that there's no difference between experimental treatment, which is the known facts, the claim that we know previously. Then alternative hypothesis, a statement that's mutually exclusive with the null hypothesis. So the term is mutually exclusive, which means if null hypothesis say yes, alternative have to say no. Both cannot agree on the same. And if null hypothesis and alternative hypothesis is the same, then we don't need to test the null hypothesis no more. We already have one answer, so we finish. So as we mentioned earlier, the goal of an experiment is to find a start evidence to either refute or nullify the null hypothesis. So our goal is either to reject or accept null hypothesis. Now, if we reject the null hypothesis, then we have more support for alternative hypothesis. And everything is based on the level of significance and the p-value. So hypothesis should specify the independent variables and dependent variables also. So with the research hypothesis, as we mentioned, independent variable always will determine the dependent variable. So independent variable here, we say the factors of interest or possible cause. Independent variable will cause the dependent variable problem. So the outcome of dependent variable depends on independent variable. So the factors of interest or possible cause of the change in the dependent variable. And the dependent variable will be the outcome or the effect of the interest. As we said earlier, smoking of cigarette causes lung cancer. So smoking will be my independent variable because it causes the lung cancer, not lung cancer causes smoking of cigarettes. So in a human-computer interaction field, typical independent variables, there can be so many, but this is just a few examples. Here we say that those that are related to technology, so the independent variable here can be the device you are using. Let's say I'm using mouse or keyboard. So types of technology or device and the design of it. So independent variable again in medical field can be the behavior of the patients, the characteristics of the patients. Here also we mentioned since human-computer interaction, a person is going to interact with the computer system. Then we can consider the age of the users, their gender. As we gave example of a computer game played by 6 to 12 years old kid. Those are all the age, the gender, their computer experience, knowledge, or if they are professional, their professional domain, we consider the education. So all this will be, again, independent variable in terms of the users of the system. And we also said those that are related to the context of use, we have a physical status. Physical status can be the person, age, actually same as what we have here, the status of the person. And also maybe people that associate with him, maybe friends or family. We also have user status and also social status. Can be income, again, the rest. So this is also typical dependent variable in human-computer interaction. Of course, almost here we will say generally in computer science applications, efficiency is very important. And also the computer resources. So the time the computer will perform whatever task, even if it's a game, the objective of the game we have to consider. Sometimes in game, we want to make the game more complicated so that it will be more interesting. Users may think more. So the AI playing with the human, maybe we need to give him more brains, let him have more ways of choosing some tasks that will trick the person. So again, that would be the efficiency, the time and the speed. And also we will say the storage devices, because here also, since it's an application, the computer resources, I think speed is number one, which is the Microsoft, I say Microsoft, the CPU, the central processing unit, the speed, and also the storage. Those are the two major computer resources when we are developing algorithm. Don't use too much storage, but go very fast. Then we have a perfect system. Also, the accuracy will be considered, so it can be a dependent variable. Thus, the independent variable that we have reduces the accuracy of the system. We also have a subjective set. Yeah, this will be based on personal perceptions, what you perceive, satisfaction. So we can measure this in a Likert scale ratings, maybe from 1 to 5, 1 to 3, very good, not too good, etc. Then also ease of learning. So that can be a dependent variable, the learning curve of the system. For example, in computer science, when we are developing a system, we may consider two major things, the speed and the security. So if I develop a website or an application to a government agency, they won't consider the speed too much. Security is number one, because as we know, many countries around the world attacking each other. The one way one country wants to get into one country is go to cyber. Again, that's why we have the cyber security, go online and try to invade on government side. So security is number one. Speed is not an issue too much. But if I'm developing a system to a non-governmental organization, let's say non-profit organization, well, they will consider more speed because they don't have anything to hide. If you like hack their system, tomorrow they bring it back to work, they continue their work. There's no profit in the organization, no, and just helping, maybe it's a foundation for helping the website. So those are the few dependent variables. It can be more than this, but this is just a few examples in terms of human-computer interaction or computer science. Now, we have three components of an experiment. We have the treatment. Treatment also can be the conditions. So in terms of our computer science, the different techniques or devices or procedures that we want to compare. It can be an algorithms, it can be a device. So yeah, the explanation here is based on computer science field, but not in terms of medicine or social. Then units can be the objects to which applied experiment treatments are applied. So if it's applied to participants playing game or something, yes, normally human subjects, participants, or with specific characteristics. So it will be gender, age, or computing experience. So you have to be participants who are testing the computer game using some different form of interaction with the computer. That's user interaction with the computer system. Now, in any experiment, we know randomization is very important, because in randomness, what we do, we give everybody, or if there's a participant, we give every participant fairly equal chance to be chosen or to be used for some specific task. Also, if it's a device or some numbers that we generate using computer system, we want it to be randomized. We don't want you to use a computer algorithm that will select a specific range of values and doesn't select on a range of value. So every study is, I think, random is very important. Randomness is very important. So here, randomization means the random assignment of treatment to experiment units or participants. It can be the experimental units or the actual participants of the experiment. You have to, in this sense, there's fair treatment for every element in the experiment. So we say in a totally randomized experiment, no one, including investigators themselves, is able to predict the condition to which a participant is going to be assigned. So nobody knows it. It generates randomly. So we can have a random table, or we can even have a software that will generate the randomization process. Also, we talk about the significant test in experimental testing. So this is, again, hypothesis testing. So why do we need significant tests? Here we say when the values of the members of the comparison groups are all known, you can directly compare them and draw a conclusion. No significance test is needed since there is no uncertainty involved. So in this case, I don't need hypothesis testing. If when the values of the members of all the comparison group are already known, then we can do our comparisons and draw our conclusion. But when the population is large, well, we can't take information or data from all the population. We are going to use a sample. So we can only sample a subgroup of people from the entire population. So this is where hypothesis testing can. As we mentioned earlier, we have a population we know in 1970, their weight is so amount, 120 pounds. Today, I want to do the same population test if their weight is the same. Well, it's difficult if I can be able to take the data from all the population and find the mean, then I don't need any hypothesis testing or significant testing. But in New York, maybe our population is over 10 million. May it will take me some time and not only time, but it will take me a lot of funds to finish taking data from all the population. So I may take a sample out of the 10 million, I may take a sample of only 200. Only we will have to make sure the sample is well representing the whole population. Then there we do our significant tests on the sample. The result we get, we generalize it to the whole population. So that's the main reason why we do significant testing or hypothesis testing, because we use a sample. It's easier to collect a sample data than to collect population data. So significant tests allow us to determine how confident we are that the result observed from sampling, the result that we get from the sample population, can be generalized to the entire population. So that's the main reason why we do hypothesis testing. So we mentioned before there's type 1 and type 2 errors when we are doing significant testing or hypothesis testing. Type 1 error is related to the p-value, and type 2 error is related to beta. And the goal of, again, type 1 and type 2 error is to reduce what we call the false positive. False positive means, again, here we say what is false, which means we are rejecting. Positive means it's true. So type 1 error means we are rejecting a correct null hypothesis. Why type 2 error means false negative, we are accepting. We say refer to the mistake of not rejecting. That means we are accepting the null hypothesis that is false. So that's why always when we look for the p-value, when the p-value is very low, lower than the level of significance, then we do what? We reject the HO, because if the p-value is very high, that means HO is good, is true. So again, we'll go through this more details somewhere along the line. But again, type 1 error, also called a false positive, refers to mistake of rejecting the null hypothesis when it is true. So type 1 error is here rejecting true hypothesis and should not be rejected. Type 2 error refers to the beta error. or false negative refers to make the mistake of not rejecting the null hypothesis when it is false and should be rejected. This is the main reason why our p-value is always when it's very, very small, preferable when it's less than 1%. I mean, 10%, 10%, 0.0, 0.1, sorry, 0.1, 10%. Most of the time, we set our confidence interval by default if we have taken inferential statistics. We always use a 95% confidence, which means the level of significance is 5%. Even to find a z-value of 5%, alpha is 5%, it's always 1.96. It's something we do a lot in statistics when we're doing hypothesis testing. So type 1, type 2 error, we have a reality. Here we say about jury decision. If you are found not guilty and you are not guilty, that's good. Sorry, if you are not guilty and you are found not guilty, is good. So not guilty and not guilty, good. If you are guilty and you are found guilty, then that's good. That's what we want. We don't want type 1 error and type 2 error. Type 1 error means you are not guilty, but they find you guilty. Then type 2 error means you are guilty, but they find you not guilty. And sometimes we can use this to create what we call the confusion matrix. Confusion matrix in data mining, we can have the sensitivity test and specificity test. Sensitivity test means, for example, the COVID-19 test is going on, we have a testing kit. Sometimes, actually, I'm negative, but when I go and test, it gave me positive, or I'm positive, when I go and test, it gave me negative. So the correct percentage of positive test is called sensitivity. The correct percentage of negative test is called specificity. Normally in medical and public health, they use that terms a lot, but they also construct the same table as we can see. So if it's a positive test and you are positive, then it's sensitivity rate. So the number of positive divided by total people that were tested will give you the sensitivity score. Always less than 1 or less 100%, which means the result, the testing kit is accurately correct 100%. So again, type 1, type 2 error, here we say it generally believed that type 1 errors are worse than type 2 errors. Why type 1 error is worse? Because again, I'm doing what? I'm rejecting something that is true. That can be more harmful than accepting something that is false. Again, according to statisticians. So here they say statisticians call type 1 errors a mistake that involve gullibility. So which means that type 1 error may result in a condition worse than the current state. But type 2 error can cause the opportunity to improve the current state. So type 1 error is more serious. And as we said earlier again, type 1 error means rejecting. Refers to the mistake of rejecting the null hypothesis when it is true. So something is true and you reject it can be more serious than something is false that you accept it. Again, this is based on the studies that has been done on different type of research tasks, and they came up with this idea. So controlling the risk of errors. I think we almost finished. I think it's time now, but let's see. Yeah, almost finished. Only 2 slides left. So please bear with me. We have a minute past. We should finish in the next 2 minutes or 3 minutes. I'll make it. So here we are talking about experimental studies using the significant testing. So we always need to control the risk of errors. So in statistics, the probability of making type 1 error, as I said earlier, depends on the p-value, or it's called alpha, or significant level, the p-value. The probability of making type 2 error is called the beta. Normally we write 1 over 1 minus beta to find the probability of avoiding type 2 error. And in statistics, we solve this problem a lot with our using the formula. P-value, you will get it from the, again, depends on the type of testing you are doing. If it's, for example, z-test, then I'll use the standard normal table. After I get the z-score value always is the sample, average of the sample minus the population. Let's say we are finding the mean, testing the mean of population. So 1970, the mean weight of the population is 120. Today, we are testing it if it's greater than that amount, and we take a sample. The sample we take, we find the mean of that sample. So we use that, the mean of that sample minus the population mean of 1970, divided by the standard deviation of the 1970 data. The answer will give you the z value. Then you go to the standard normal table to go and find the p-value. Now, if the p-value is greater than the level of significance, which is the alpha, then we are going to accept HO. If it's less than the level of significance or very, very small, then we reject the HO. Then next we can find the probability of avoiding type 2 error. But always, mostly in hypothesis testing, we really don't find a type 2 error unless we need it. Type 1 error is the problem, because when we get the P will determine the type 1 error. So if P is very, very small, it seems we are, that shows us that we avoid type 1 error, then we reject HO. But when the P is very big, say greater than 10% or greater than the level of significance, then we have to accept the HO. We don't want to reject HO. If we reject HO, in that case, we get type 1 error. So that's the whole concept. As we said earlier, you can see the p-value most of the time is 0.05, which is 5%. We see in statistics textbook always confidence level or interval 95%. If it's 95%, it means the error sign, the p, will be 5%. So alpha and beta are interrelated. Under the same condition, if I decrease the alpha, it will reduce the chance of making type 1 error. And that's our goal. That's why p-value always have to be very small to reject HO. But if we decrease alpha, then type 2 error increase the chance of making type 2 error. Because if alpha is decreased, p is decreased, the probability, then what will happen is that the beta will increase. So they're interrelated on the same studies. So in the experiment, we say that it's generally believed that type 1 errors are worse than type 2 errors, as we said earlier, because we are going to reject something that is true. And always the p can be as low as 0.05 or lesser. So this is the limitation of experimental research. It requires a well-defined testable hypothesis that consists of limited number of dependent and independent variables. Also, the strict control of factors that may influence the dependent variable. Now, if it's a lab-based experiment, it may not be good a representation of users, typically the interaction behavior. Because we know an experiment in the lab, we put X, we see what will be the Y. We don't go forth and come, there's no much interaction. And that will be the conclusion. Again, thank you for your time. We are like 6 minutes more than our usual time. So I'm going to turn off the recording and see if we have any question before we leave. Again, I'm going to post this recording in the classroom.